A very good evening, sir. This is Suryansh Khemka, 20 BCE, 1469, here to represent my video for the DA-2, and my topic is Turing machine and its application. So what is Turing machine? Turing machine was invented by Alan Turing in 1936, and it is used to accept recursive enumerable languages generated by a type 0 grammar. The Turing machine is a mathematical model of computation that defines an abstract machine that manipulates symbols on a strip of tape according to a table of rules. Despite the model's simplicity, given any computer algorithm, a Turing machine is capable of simulating that algorithm's logic can be constructed. The Turing machine consists of a tape of infinite length on which read and write operation can be performed. The tape consists of infinite cells on which each cell either contains input symbol or a special symbol called blank. It also consists of a header pointer which points to the cell currently being read, and it can move in both the directions. This hypothetical machine is thought to operate an infinite memory tape, the kind that was used in the early days of computing to store data. Data is represented on this tape on discrete cells, and the machine reads these cells to understand what data is stored there. The machine can take multiple actions. It can either write a symbol over one of the cells, move right or left to read right on the adjacent cells, and process the information present in the cells and take the relevant actions. Through this mechanism, any logic algorithm can be decoded onto this machine and can be used to test the veracity or feasibility of the algorithmic logic. It can be used to check if the logic gets stuck in loops or if a certain part of algorithm gets executed the way it's expected to. So what are the features of Turing machine? There are various features of Turing machine. It has an external memory which remembers arbitrary long sequence of inputs. It has unlimited memory capability. The model has a facility by which the input at left or the right on the tape can be read easily. The machine can produce a certain output based on its input. Sometimes it may be required that the same input has to be used to generate the output. So in this machine, the distinction between input and output has been removed. Thus, a common set of alphabets can be used for the Turing machines. Next, we are going to see the application of Turing machine. Turing fulfillment can be estimated for an arrangement of guidelines in light of how they can recreate a Turing machine. For instance, a programming language that can hypothetically communicate all undertakings unaccomplishable by PCs is supposed to be Turing finished. As of late, specialists at Harvard University have made what is named as a synthetic Turing machine, essentially a tank of synthetic compounds that can hypothetically work as a PC. To make this cutting-edge understanding of a PC, scientists have utilized the model of Turing machine to devise this compound PC, with the distinction being that this PC utilized synthetic substances rather than memory tape to store information. They have formulated this framework utilizing a memory class of refined water, and it acknowledges input as different synthetic substances which have each been credited to an information image and will be dropped into the container. To place this Turing machine in real life, the analyst concocted a compound language in view of existing Turing machine model of language called L3, containing the letters A, B, and C. Words can be made through equivalent blend out of letters set up in sequential requests like ABC or ABBCC. With this language, it is supposed to be Turing finished and can be utilized to tackle complex issues. When it can perceive inappropriate blends, it can go about as a completely substantial, broadly useful PC. It's a genuinely basic framework like the Turing machine. However, what it shows us is enormous. They have attempted to discover replies about the beginning of the life of the planet and how an intricate compound processing framework, for example, this might have prompted the ascent of aware animals. Power of Turing machine. Turing machine has a great computational capabilities, so it can be used as a general mathematical model for model computers. Turing machine can model even recursively innumerable languages. Thus, the advantage of Turing machine is that it can model all the computable functions as well as the languages for which the algorithm is possible. Limitations of Turing machine. Computational complexity theory. A limitation of Turing machine is that they do not model the strengths of a particular arrangement well. For instance, modern stored programs computers are actually instances of a more specific form of abstract machine known as the random access stored program. An experimental prototype to machine or RASP machine model. Like the universal Turing machine, the RASP stores its program in memory external to its finite state achieve Turing machine's extraction. The RASP's final state machine is equipped with the capability for indirect addressing. The RASP program can address any register in the register sequence. The upshot of this distinction is that there are computational optimizations that can be performed based on the memory indices, which are not possible in a general Turing machine. Thus, when a Turing machine are used as the basis for bounding running times, a false low bound can be proven on certain algorithms running times. An example of this is binary search, an algorithm that can be shown to perform more quickly when using the RASP model of computation rather than the Turing machine model. Concurrency is the other limitation of Turing machine. They do not model concurrency well. For example, there is a bound on the size of an integer that can be computed by an always halting non-deterministic Turing machine starting on a blank tape. By contrast, there are always halting concurrent systems with no inputs that can compute an integer of unbounded size. How is a Turing machine expressed? Turing machine is expressed as a 7-tuple QTB sigma delta Q naught F, where Q is a finite state, E is the tape alphabet systems which can be written on it, symbols which can be written on tape. B is a blank symbol. Every cell is filled with B except input alphabet initially. Sigma is the input alphabet, symbols which are a part of input alphabet. Delta is a transition function which maps Q cross T, implies Q cross T cross L, R, depending on its present state and present tape alphabet pointed by the header pointer. It will move to new state, change the tape symbol, and move head pointer to either left or right. Q naught is the initial state. F is a set of final states If any state of f is reached, the input string is accepted. Properties of Turing machine. Turing machine can recognize and decide different kinds of problems and languages. Languages describe problems. For example, there is a language of all strings made up entirely of ones. Some members of this language would be 1, 1, 1, 1, 1, 1, 1, etc. One could make a Turing machine to compute these strings. For example, write a program that just makes the Turing machine write a 1 each time it moves to the right and have it do so the machine always moves to the right. Recognizability. A language is recognizable if a Turing machine accepts when an input string is in the language and either rejects or loops forever when an input string is not in the language. In other words, if a language is recognizable, these are the strings not in the language for which the Turing machine may not halt. Decidability. A language is decidable if a Turing machine accepts strings that are in the language and rejects the strings that are not in the language. In other words, the Turing machine will halt on all inputs. All decidable languages are recognizable, but not all recognizable languages are decidable. The halting problem is an important example of a recognizable problem that is undecidable. Thank you.